All right, you should be recording now. All right, so the labs are going to run, actually, they're going to run usually behind the theory, or at least at the same time as the theory. You know, what you cover in the theory in a given week. Like, so for this week, we are literally starting physics. We're starting what's called kinematics. All right, and so hopefully you all have seen my lecture or chapter 1 video. You know, as I point out in the chapter 1 video, we're really starting this class. You know, when you're talking about physics, you know, it's kind of like, you know, if you remember, you know, if you ever gone to a Renaissance fair, you know, you walk in there and they'll tell you, well, it's this is medieval England in year whatever 1587, or they'll give you the exact year what they're trying to reenact, right? Well, for where we are in this class, I would say that where we are right now, it's about the year 1500. And at that point in time, there was no science. You know, any kind of technology was kind of accidental, right? It's kind of like, you know, I saw a commercial one time, and you see one guy walking, you know, two people are going to collide on a corner. One guy has a jar of peanut butter, he's eating a jar of peanut butter, and the other person's got a chocolate bar, and they crash into each other, and they get the chocolate bar and the peanut butter, and they realize they discover they discover the Reese's Pieces, right? Or Reese's peanut butter cups. They realize, oh, chocolate and peanut butter taste good together. That's kind of like how science was done. Oh, these, you know, I make this kind of metal that's stronger than anything that I've seen before. There was no, you know, chemistry or physics per se. It was just, you know, it was kind of like science by trial and error. All right, and so now what we in this chapter, you know, in around, you know, in the 1500s, about 1564, Galileo came to exist, and again this time we're also coming out of the Middle Ages, coming into the Renaissance. All right, and so the Middle Ages was a time when in Europe, you know, it was about 1,000 years where nothing got accomplished, and they call it the Dark Ages. And with the invention of the printing press by Johann Gutenberg, when people were able to have mass printing of books and then mass printing of pamphlets and ideas, revolution started forming, not just in science, but also in philosophy, in politics, and also in religion. You know, various, you know, people started asking questions. You know, what's the authority of the Catholic Church, for instance? You know, I mean, so you start having Protestantism. People started asking questions about what's the authority of a monarchy. People, you know, we started seeing the developments of democracy and also developments of communism, right? And so, while at the same time, ideas in science started to flourish, and people started asking questions. And the first and foremost of these great minds was Galileo. So chapters 2 and 3, and really this lab, is about what Galileo accomplished, right? And so it was Galileo. Oops, 1 second. Brandy pen. Galileo Galilei. And I think he was born, I believe, in 1564. He died in 1642. He died this exact same year that Sir Isaac Newton was born. And so it's kind of interesting how it all kind of works out. Galileo, many people have referred to him as the father of science. He's the first person to really start asking questions. Now, Galileo developed, you know, the field of mechanics, and we're studying the theory of mechanics. And he developed theory of mechanics that he developed, I would say, the earliest part of mechanics, called kinematics. And that's what this lab is about. All right, so kinematics is the study of objects in motion without regard as to why the motion. Okay, there's no question. There's no reason as there was no understood reason as to why objects would move the way they do. No, they just do. Now Galileo, I'm sure, was curious as to why bodies moved. Or I guess I should say, should be more specific. Say bodies. This is part of the theory of mechanics. We don't know why objects move at this point. We don't ask that question yet. So in chapters 2 and 3, we don't yet ask that question. It's not because Galileo did not know, and it wasn't because he wasn't curious or did not want to know. It's just because the human race did not have any understanding of what is called the laws of physics. The laws of physics are the reason why objects move. And so there was no knowledge of the laws of physics at that point in time. It was Isaac Newton gave us the laws, even the concept for humankind, the laws of physics for the first time ever. And we can almost, if we were to ask the question, who is the most significant person who ever lived to the human race? I mean, many people may not necessarily think that Isaac Newton would be the answer. And I would, my vote would be Sir Isaac Newton. Why? Because Isaac Newton brought to humanity the concept of the laws of physics. And with the laws of physics, not only do we understand mechanics and gravitation, in Newton's work, but other scientists could ask the question, well, might there be laws of physics for other phenomena like heat or temperature or electricity, magnetism? And indeed there are. So our very technology is in place today really because of the work by Isaac Newton. And so it's the laws of physics, the 3 laws of motion and the conservation of energy that really drives why objects move. But here we are in the very beginning, and so essentially the way theories work, at least in this particular course, is you're going to observe phenomena first, and then you figure out why the phenomena. And we're going to have the same approach when we talk about thermal physics. So when I look at it right now is that, when you come to this class, the only thing that I assume is that is your mathematical background. I don't assume anything else. I mean, literally, like about a year or so ago, I started teaching this. I taught this. I've been teaching this class since 2017, but about a year ago, we had a set of homes, luxury homes, being built across the street from our neighborhood. And you saw the plans of these great, majestic luxury homes, and all this, what was going to be. However, at the time when you looked across the street, all you saw was dirt, mounds of dirt with tractors pushing it around. You knew there's going to be great luxury homes, but all you saw was dirt being pushed around. And so that's kind of where we are right now. We're basically pushing around dirt. We don't really have a theory. We're trying to figure out a theory. And so again, I cover all of this in a chapter 2 lecture, right? But that's what this is kind of about, is that we have to define the vocabulary that we're even going to talk about. And so to kind of start off, you're talking about a study of, objects in motion. You have to first of all have a way of knowing where an object is. So we have the concept of position. Where an object is. In fact, before you even have that concept, you have the concept of a coordinate system. You have to lay down. So like in chapter 2, it's one-dimensional. In chapter 3, we go into 2 dimensions. You have to specify a coordinate system. A coordinate system in 1 dimension simply just looks like a real number line. So you say, I'm going to call this 0, and I'm going to say this is 1, 2, 3, whatever. And essentially, you need to be able to lay out, where, what reference, where can you mention, where can you officially state where an object is even located? We call that the position. So we say an object is sitting here at let's say at 3. We would say we would draw a position vector from the origin. It's kind of hard to see it in 1 dimension, but we draw a vector. And again, we talk about vectors in chapter 1. We draw a vector that extends from the origin to where the object sits at 3. All right. And again, we call that the position. Where is the object in this coordinate system? You know, the coordinate system that we use and mostly in this class is what's called the Cartesian coordinate system. So called the Cartesian coordinate system, and it's named after Rene Descartes. You know, the story goes Rene Descartes was lying on his bed looking up at the ceiling, and he saw a fly walking around. And he thought, where is there a systematic way that I can locate this fly on the ceiling? And so he kind of developed, you know, the whole grid, you know, the two-dimensional coordinate system, the X and Y. And so we can say that you know, we have we named, you know, the coordinates. I mean, basically, he was the first person to really come up with the concept of a coordinate system. All right, and so we lay down a position. We want to talk about an object going from one position to another. We call that the displacement. So in vector terminology, we call the position X. We'll call it, you know, like let's say X, you know, X is a position. Well, let's say it moves from one position to another. That would be called the distance or the displacement. And let's see, that would be delta X, change in X. Remember, delta means change. That would be X2 minus X1. Again, to get a more complete description of all this, please watch the chapter 2 video. But again, we have to lay down and say, okay, well, we have to understand where an object is. And again, I put these vector hats on it. I mean, really, you know, don't have to really worry about that. Vector has so much of one dimension. A direction is nothing but the direction of a vector is given by a direction and a magnitude. A direction is either to the right or to the left in one dimension. All right. Magnitude would be if I took out, you know, a measuring tape and I measured the length of the vector. All right. So anyway, we refer to the speed as the magnitude of the displacement. Again, you get a more complete description of this in my video. But the magnitude, basically, when you look at a number, you know, one of the things they don't tell you in your math classes is that when you hit the absolute value of something, so we would call the speed, we would say the speed, or sorry, not the speed, the distance. The distance, well, the distance is really, you look at it, you say, well, the distance would be given as, we would call it d, and that would be the magnitude of the displacement. You notice we use the exact same absolute value bars that we do in your math class, and there's no accident there. You talk about absolute value, you know, a number, a real number has two parts to it, a sign and a magnitude, right? So a real number has a sign and a magnitude. Right, and so when you take the absolute value, you literally strip off the sign. It is signless. You get the magnitude. So the absolute value sorry, I'm going to throw my whiteboard here. All right, the absolute value, strips off the sign and gives you just the magnitude. So, all right. So the absolute value of a real number strips off the sign and gives just the magnitude. So it's signless. Now, I've heard teachers in like junior high and high school say, well, when you take the absolute value, if it's positive, you leave it positive. If it's negative, you make it positive. Well, that's wrong. The fact of the matter is, it's neither positive nor negative. It is the magnitude. You've literally stripped off the sign and you've left the magnitude. So for instance, I have a twofold ambiguity. If you tell me I have a number that has a magnitude of 3, it could be positive 3, but it could also be negative 3. Both of these, if you take a look at it, if I were to get all the measuring tape, I could say, well, this has a magnitude of 3 and this vector has a magnitude of 3. Both of them do. So if you tell me I have a number that's a magnitude of 3, which is it? Is it positive 3 or negative 3? Right? Again, 3, a magnitude of 3 has no sign, S-I-G-N, sign, right? So again, we start developing our vocabulary. We have displacement, would be the difference in positions. We have distance, which is the magnitude of the displacement. When we start talking about motion, so Galileo, looks upon the world and he sees that things are in motion. How do you define something that's moving? Well, Galileo, again, this is something we take the concept of time for granted, but it's not obvious. How back in the 1500s, it's not obvious. What the cadence of the universe is. We did not even have the second that we so depend on today. We didn't even have that really well defined. We didn't understand. I mean, NIST has, the definition of a second, depending upon the number of fluctuations of a cesium atom, right? I mean, it's defined. There's a very, very metastable state in the element cesium, and it literally defines the second so precisely, based upon the quantum state of a cesium atom, right? I mean, but we didn't have that kind of technology, so we didn't really understand exactly what a second was. We understood seasons. We understood that, that there was days, there's day and night, and we understood that there were seasons. It was, winter, then spring, then fall, then winter again, and so on and so forth. We understood these. We understood a concept of a year, but we didn't really understand things to such a precision like a second or even parts of a second, right? So the concept of how things move and what is the cadence of the universe, that may seem obvious to us who live in the 21st century, but it's not obvious at all if you think about it more deeply. So you look at this and you say, well, how would you define something moving? Well, you define it in terms of what's called a velocity. So the velocity is literally given by the change in the position or the distance divided by a change in time. So again, that is how you define your velocity. Now, is that a good definition of velocity? I mean, is that the instantaneous velocity? Well, I'll give you an example. I can say, okay, let's say, I'm at work and I leave my parking lot and somebody has a stopwatch and says, okay, you're leaving the parking lot at such and such a time, you're heading home. And they can say, okay, well, we'll call that time, we'll say you're at position X0 and you're at time T0. Now, I travel home. And let's say we know where my position, home is. I get home and I'm at position X1. And somebody has a stopwatch there and says, yep, it is now time T1. So let's just say, for instance, we happen to know that, well, let's say X1 minus X0, we'll say it's 20 miles for easy numbers, 20 miles. And we'll say that, when someone does the stopwatch and say, oh, T1 minus T0, we'll say it's a half an hour. All right, so let's calculate the velocity based upon that. We would say, oh, the velocity would be X1 minus X0 divided by T1 minus T0. What would that be? Well, the change in X, what's that? I told you it's 20 miles. And we say that I traveled in a half an hour. The difference in time is a half an hour. So I would come up with 40 miles per hour. Now, I traveled on surface streets. I traveled in my company's parking lot. I traveled on the freeway. Did I always travel at 40 miles per hour? No way. I mean, first of all, there's no way I could travel 40 miles per hour in a parking lot, maybe on the surface streets. And it would be probably very, very unwise for me to travel 40 miles per hour in a freeway. So yes, you might do this calculation. You might come up with the idea that I travel 40 miles per hour. But what this really is telling you here, this is really not the velocity at any given time. This is what we call the average velocity. I can put an over bar on that. So this is really the average velocity. What I have calculated here is the average velocity. Okay, it's not the instantaneous velocity. It is the average velocity. How do I do better? Well, let's say I want to figure out the velocity of my velocity, or let's say we want to measure my velocity when I'm crossing a certain freeway road sign. What might you do? Well, you might have somebody stationed 100 or maybe a couple hundred feet before the road sign, and maybe somebody stationed a couple hundred feet after the road sign. And you know the distance from, distance between the two people, and you have your stopwatch, and you get a better measurement. What have you done? You've taken the time duration, you've made it smaller, trying to get a better understanding of what my actual velocity is. But even then, I might have put the brakes on a little bit. I might have sped up. I mean, there's no guarantee that that's my perfect velocity either. What you have to do is you have to actually employ calculus. Now, I've told you that in this class, this class does not use calculus, but I will tell you where you fall short by not having university physics, having college physics instead. And where you need it, and here we are, we're only in chapter 2, and we're already realizing that we really need calculus. What you need to do to get the instantaneous velocity, and I'm gonna drop the little vector hats. But why calculate was the average velocity? What you need to do is you need to take smaller and smaller time intervals. In fact, you need to take time intervals that are so small that they're infinitesimal. They're infinitely small. And so what I mean by that is if I want the velocity right now at a certain time, I need to take what's called the limit. The limit, as my time duration gets smaller and smaller, it gets so tiny, so thin, it approaches 0 of delta x over delta t. And that's calculus. We call that the first time derivative in calculus. We refer to that as dx dt. In calculus, we would call this the first derivative of the velocity with respect to time. That's what we would call it. First derivative velocity. First derivative of the position with respect to time. That is the velocity. Okay. We call that the instantaneous velocity, the velocity right now. Instantaneous velocity. So for you to know what the velocity is right now, you need to employ calculus. All right. Now we can go further and say, well, I know that clearly the velocity must change too. Because in my example, I didn't always go at 40 miles per hour. Maybe I went through 40 miles per hour. I mean, I started. I was in a parking lot. I was at 0, and I probably got up to the freeway. Maybe I got up to 70, but my velocity changed as well. There's a concept of the change in velocity with respect to time. All right, and so that concept is called the acceleration. So in the same kind of token, we would say the acceleration, it's a vector as well. It's the change in the velocity with respect to time. And again, for the same reasons, given that the acceleration can change instantaneously, I would need to employ calculus there as well. So for the same reasoning, the true acceleration would be the limit as the time duration approaches 0 of the change in velocity with respect to time. And I would refer to that as dv dt. Again, this would be the first derivative of the velocity with respect to time. Okay, and again, this is for me to know what the acceleration is right now if the velocity, if the acceleration changes. Okay, now now there's certain names, for instance, like you take velocity. If I want the magnitude of the velocity, that's called the speed. And it's the same kind of thing. I would take absolute value bars around the velocity and I would get the speed. When I take the magnitude, I take the hat off. You know, in vector notation, you know, the vector hat, that's the vector has a magnitude and a direction. If you take off the hat, that's a way of saying that that's the magnitude. All right. So if I say I want the magnitude of the position, or I should say magnitude of the displacement, that would be, I take the hat off. That would be the distance. All right. So again, this is the nomenclature for mechanics, or for, you know, well, actually for mechanics, but for kinematics and for this lab. Now, any questions so far? We're literally pushing around dirt. We're trying to we're trying to make a theory that discusses or that governs how bodies move. So you have to ask the basic definitional questions of what would that theory entail? Well, I need to know where the object is. That's called the position. I need to know how the object moves from one position to the other. Now, the difference of that's called the distance. The magnitude of the distance. I'm sorry, that's called the back up. How an object moves from one position to the other is called the displacement. The magnitude of the displacement is the distance, and then we need to know how the object moves in time. So the change in the position with respect to time is called the velocity. The magnitude of the velocity is the speed, and the change in the velocity with respect to time is called the acceleration. Okay, these are all, you know, terminology that we now need to understand. Now, and you'll see this in my lecture video, but in this with these relationships, these relationships, these particular variables are all related to each other. And so let's kind of see how that works. So let's imagine for a moment that I consider situations. Well, let me put it this way. If as I told you earlier, I define the average velocity as just the change in position with respect to time. All right. So I know I've told you, I've shown you through an example that that's the average velocity. Change in position or displacement over a interval of time. What's another way that I can write an average velocity? Well, another way I could write an average velocity would be, well, actually, let's see here. I can also write an average acceleration. Same thing. Average acceleration would be the change in the velocity with respect to time as well. Now, one of the things that we're going to assume in this class, and it turns out it's a very good assumption, is we are going to consider constant acceleration. In mechanics. We're going to assume that the acceleration over the interval that we're discussing is constant. Now you might say, well, is that any good? What kind of assumption is that? Well, it turns out that it is good because we're going to talk about Newton's second law that says that force and acceleration are directly proportional to each other. You know, when we talk about Newton's second law in a rough form, we say F equals ma. Again, that's not the exact Newton's second law, but I mean, again, I'm not there yet. But you notice that the acceleration is if I have a constant force, I have a constant acceleration. It is very easy to understand the concept of a constant force. So you have a constant force, you have a constant acceleration. So where does an acceleration come from? Well, oftentimes it comes from a force. Many times you can apply a constant force over a time interval. That is definitely something that you can do. All right, and so the concept of a constant acceleration is not such a hard concept. Give me a moment, please. I'm sorry. Hello. Hello. Can you call your mom? Sorry, daughter's calling me. All right, so let's see, where was I? Oh, yes. So you have a constant force. You have a constant force gives you a constant acceleration. That's why it makes sense. We're not really here yet. We're chapter 4 is where we talk about Newton's second law. So we're going to make the assumption that the acceleration is constant. All right, and so going upon this last equation that I just got them putting down is our acceleration, our actual true acceleration, is actually going to be the change in the velocity with respect to time. All right, so we break this out. We say, well, that change in velocity, I'll say, is the velocity at some later time minus the initial velocity divided by that later time minus the initial time. All right, so again, v is the velocity at time t, and v naught is the initial velocity at initial time t naught. And when I put a little O here, oftentimes when I say initial, we oftentimes refer to this as naught. So I would refer to this right here, I would call this T naught. Nomenclature that physicists use. So we could say T sub 0, but oftentimes it's T naught. So essentially what I'm saying is the acceleration is constant. It's not just the average acceleration. I mean, again, if something's a constant, its average is going to be the same value. I mean, if I tell you that, something is constantly has a value 2, it means anytime I look at something, it's going to be 2, 2, 2, 2, 2, 2. If I add a whole bunch of 2s and divide by the number of them, I'm going to get an average of 2. So if you have something that's constant, its average is the same as that constant. All right, and so again, instead of having an average here, I can take off the over bar, which means average, take that off, and I actually have what the acceleration is because I'm assuming the acceleration to be constant. I'm also going to assume that I start my stopwatch at 0. And again, there's no loss in generality for me to do that. I can start my stopwatch anywhere I want. So I can assume that T naught is 0 without any loss in generality. All right, so again, we can assume that T naught equals 0 without loss of generality. Essentially, we can start the stopwatch of the problem to be 0. I mean, I can dictate what time the problem starts. So I'm going to call it 0. So that means that in this above equation, I can essentially erase this. What I have is just A is equal to v minus v naught, all divided by t. And so what I can do is I can kind of rewrite this equation up here and say with the concept of a constant acceleration. Drop my eraser. There it is. I can write this in the following manner: that A is v minus v naught, all divided by t, and I can cross multiply, and I can write this as v equals, or so v minus v naught equals at, or I can add v naught on each side, and I can write a kinematic equation: v equals v naught plus at. I mean, that is our first constant acceleration kinematic equation. So essentially what this means is that I have initial velocity, I have a constant acceleration, I wait a certain amount of time, and I get a final velocity. This is a linear equation. What this means is that if I were to graph this, actually time is always positive. If I were to graph this, I have some sort of initial velocity v naught. Let's say this is the velocity and this is the time. Say this is v naught right here, and it ends up forming a line. And so as time progresses, and then the slope of this line is the acceleration. The acceleration is the slope of that line. All right. In fact, a derivative in calculus is a slope. The acceleration is the slope of the velocity. Velocity time curve is the slope. All right. And so again, this is a valid relationship in physics. V equals v naught plus at. All right. So again, I could write this as a kinematic equation. And again, this is something we're looking at in this lab. And so we say that v equals v naught plus at. If the acceleration is a constant, then the velocity is linear, right? So again, a is constant acceleration. There is a linear relationship between velocity and time. And the slope of the velocity time graph is the acceleration. All right. This is one of the kinetic equations that you will use very often. It's one of the equations that'll be in your toolbox for doing kinematics problems. Now we need some more equations. So let's take a look now at another situation here. So again, I'm going to kind of leave this equation up here. Now let's go back to our relationship for the relation between the velocity and the position. So now what I told you earlier was that the average velocity was the change in position with respect to time. And I told you that earlier. All right. And so what that, again, I have to use differential calculus in order to actually tell you what the instantaneous velocity is. But let's just kind of go with this for now. Let's cross multiply. And so we would say that delta x is v bar delta t. I mean, I'm just doing cross multiplication there. What is delta x? Well, delta x is x at a later time t minus x naught at the initial time. X naught is the position at the initial time. And that's equal to v bar, that's the average. And what is the average? Well, you have the average is always going to be take two values, add them up, and divide by 2. Or when you take an average of something, as I talked about last on Tuesday, you add up all the values and divide it by how many values there are. So I can take an average velocity. I only know 2 points. I know the initial velocity and I know the final velocity. And I literally just take those 2 and add and divide them by 2. Want the average velocity. That's V bar. What's T? T minus T naught. So again, X is position at time T. X naught is the initial position at the initial time T naught. All right, so that's our definition. X is the position at a later time T. X naught is the initial position at an initial time T naught. All right. Now, again, as I said, I'm making the assumption I can start my stopwatch whenever I want, so I'll call T naught 0. All right, and so what happens now is this equation simply becomes, I don't have to put this difference here. I can just literally write T naught. So again, what I have is another kinematic equation that you use in this class. All right. So again, X minus X naught is V naught plus V all divided by 2 multiplied by T. Again, that's another kinematic equation of constant acceleration. And to this lab, we need one more kinematic equation. All right, so we have those 2. And finally, let's combine the 2 and we'll get the third one that we need. There's actually 4 kinematic equations used in this class, but I'm just going to give you, actually there's 5, but I'm just going to give you the 3 that you need. Watch the lecture to get the other ones. Again, it gives you a toolbox of equations to use in order to be able to govern kinematics, basically objects in motion. What happens here if I'm going to combine these 2 equations? I have these 2 equations. Again, these are 2 kinematic equations for constant acceleration. So let's kind of rewrite this guy over here. So I have X minus X naught is B naught plus V all divided by 2. All of this multiplied by the time. Now, I'm going to take this second equation and I'm going to develop it a little bit. And what I'm going to do with the second equation is I'm going to add V naught to each side and divide each side by 2 because I can. Nobody says I can't. So what I can do here is I can say, well, I have this equation, V equals V naught plus AT. What I'm going to do is I'm going to add V naught to each side. So I have V plus V naught is going to equal 2V naught plus AT. I mean, all I'm doing is adding, again, just algebra. What I add to the left, I add to the right. So just, again, I can do that. Nobody says I can't. And then what I can do is I can divide both sides by 2. Again, I can always divide both sides by 2. Nobody says I can't. I can do that. I can't do that either. So I'll divide the left side by 2. And I'll divide the right side by 2. All right, when I do that, I end up getting that V plus V naught over 2. These 2's cancel on this first term, so I just have V naught. And over here, I have plus 1/2 AT. And all I've done is I've taken the first kinematic equation I derived, I added V naught to each side, and I divided each side by 2. All I'm doing is mathematical operation. But why am I doing that? Because I'm going to make a substitution. What I want to do is I want to essentially get rid of any description of the final velocity. And when I do that substitution, instead of writing what's in parentheses, I can then write that X minus X naught is, instead of V naught plus V over 2, I can write this instead. v naught plus 1/2 at all multiplied by t. Now I can distribute the time, and I can write that x minus x naught is v naught t plus 1/2 at squared. That is my third of 3 kinematic equations. So again, these are kinematic equations for constant acceleration. So this is the third one. So again, this is what we're going to study in this lab tonight. Again, I covered this in chapter 2 video. I'm just kind of giving you this the quickie version. And so we'll kind of write this here. So this is again x minus x naught equals v naught t plus 1/2 at squared. And there are a couple other kinematic equations that I derive in the video. I'm going to stop right here on that and just kind of give you an idea. So again, these are kinematic equations for constant acceleration. Okay, so the important thing is to consider here is that I have made the assumption that the acceleration is a constant value. Okay, and again, as I told you, that's an okay assumption to make. In fact, it's a very good assumption. I mean, it is because we'll later learn that kinematics, that things move because of forces, and it's very the concept of a constant force is not an invalid concept at all. In fact, you can definitely think of forces being applied over a constant time interval. Applying brakes on a car or whatever. I mean, so again, the concept of a constant acceleration we'll find is a foundation of mechanics. All right. So these equations, plus a couple others that I derive in the video, are your toolbox. One thing you'll notice about the various equations is that there's how many things do you know? I mean, how many things can you possibly know? Well, you could know x minus x naught, that's the displacement. You could know the initial velocity, v naught. You could know the final velocity, v. You can also know the acceleration. You can also know the time. And you'll notice that every one of those equations you see up there, plus the other two I haven't derived, and if you watch the video, they're missing two major variables, like this top one. This top one, you see no knowledge whatsoever of the displacement. All right, so if you don't know anything about the displacement, that's okay. So again, there's one thing missing in each equation. So essentially, you cannot know two things. So if I don't know the displacement and I don't know, say, the time, I can use this equation. And again, one of the things doesn't even come into play, and the other thing I'm solving for. So again, you're allowed to not know two things. One of the things doesn't, you pick the equation where the thing you don't care about out of the two things doesn't even appear in the equation, and then you solve for the other. So every one of these is missing something. So this one's missing the displacement. This one is missing the acceleration. This equation is missing the final velocity. And then you'll notice that there's an equation that that misses the time. Now the next one, if I were to continue deriving stuff, I would derive an equation for that would be kinematic equation where you don't see the time come into place. And so anyway, you figure out what you know and what you don't know, and then you, out of your catalog of kinematic equations for constant acceleration, you pick the one that is the right one for you to use for the problem. All right. Now, this is all work done by Galileo. And one of the cool things is that, again, as I said, it's not much of a stretch to say that, the acceleration is a constant. In fact, you have a really, really good example of this when you're talking about, falling objects. So in free fall, for instance, you have an example. You have a total example of a constant acceleration. That's called the acceleration due to gravity. All objects fall to the earth at the same acceleration. This is one of the things that Galileo showed. So all objects, or all bodies, fall to the earth with the same acceleration. G. And in SI units, we take G to be 9.80 meters per second squared. So what I can do is I can imagine, and I explained this in the video, I'm free to choose whatever coordinate system I want. Nature's going to do what nature's going to do, irrespective of how I watch nature. I can pick an upside down coordinate system, such that the acceleration and the velocity are all positive in this coordinate system. So I can literally say is I can write all these equations. They basically look the same, except I replace x's with y's and I replace the acceleration with g, right? So this equation, this acceleration becomes, instead of a, it becomes g. This equation, I have vertical variable y. Everything else is the same. This equation, I replace the x with y's. And I replace the a with the g. Okay, and so and you see, and what's interesting here is that this is no longer a variable. It looks like a letter, but it actually stands for a value. So when you do this, when you talk about free fall, you actually have one less variable among all the variables to consider, right? So again, that's a quickie version of the theory of kinematics. All right. Now we need that theory for this lab. Now this lab is a little different than most of the labs. I mean, when we're starting off, again, most of the labs in this class refer to, they basically depend on some software called PHET software, simulation software for the University of Colorado Boulder. That's the software we use in this class. So most of the labs, the first thing you see is a link to the software, the simulation software. This lab does not have a simulation associated with it. And so what we're trying to do is we're trying to understand the concepts of kinematics. All right, basically the concepts of applying these equations and showing that they're right. So I'm going to not worry about the free fall equations. We'll just consider the ones that are basically in one dimension with x. So as I showed you earlier today, the equations I really want to care about right now are these two. V equals V naught plus AT, and x minus x naught is V naught T plus 1/2 AT squared. Those are two equations that I want to care about in this lab. All right. So again, I went through this process because I always kind of give a little theoretical background to the lab, and I want to give you an idea as to why the data looks like it does. Okay, nothing in science occurs for no reason. Everything has a reason. Everything has a logical deduction and a reason as to why it is. And so I try to prove that in this class. Right. So there's a reason why we have this. So going to the lab write-up. Again, hopefully you have it with you. The first part is, part A is the velocity, we call the ratio of distance and time. So what you're trying to do here is in the first table, if I go to page 2, luckily this one actually has numbered pages. If I go to page 2 of the lab, the numbers are on the bottom right corner. What it wants you to do without calculating the velocity, it wants you to kind of indicate which velocity you think is the greatest. And how you do that is, you look at this table and you see set 1 and set 2. Set 1 and set 2 essentially have, for instance, set 1, the time duration, t, is 10 seconds in each one. Now, if you think about it for a moment, an object with the greatest velocity is one that's going to travel the greatest distance in a given time interval. All of these time intervals in set 1 are 10 seconds. So you literally pick the one. You have the first one says 1 meter, it gets traveled in 10 seconds. Another one is 2.5 meters in 10 seconds. Another one is 30 meters in 10 seconds. Well, let me ask you this. Which one of those three do you think has the greatest velocity without calculating? Anybody?
Or would it be the one that's 10 seconds and 30 meters?
Absolutely right. The one that's traveling the most in the same amount of time. You didn't have, again, don't even have to bother calculating there. You just kind of look at it and say, well, they're all intervals of 10 seconds. Now, what we see here is in set 2, you see a little different situation. In set 2, you notice that now the distance traveled is the same in each one, 0.2 meters. But now, in the first one, you see it took 20 seconds to do that 0.2 meters. In the second one, it took only 1 second to go to 0.2 meters. In the third one, it took 10 seconds to go to 0.2 meters. So looking at that, what do you think is the greatest velocity? Anybody?
Would it be the one?
Yes, you're absolutely right. Because given it 10 seconds, the one where the one that only took 1 second, that's the one that's going to take the least amount of time. So again, that is going the fastest. The other ones take longer time to achieve the same distance. You're absolutely right. So what I would do is I'd put a check mark to the right in the rightmost column of your choice of the greatest velocity. That's all there is to that problem. It's all I did. Put a check mark there for what you think is the greatest velocity. Now, if we go to, again, if we go to the table on the bottom of page 2 of the lab, what you now see is time durations that vary and distances that vary. So there, what you want to do is you want to calculate d divided by t. You actually want to calculate speeds. So I mean, I'll do the first one for you. It's simply, let me erase. I'll keep these equations up. Well, I'll erase these equations. So simply, all you're really calculating in table 1. Again, we start off easy in this class. You're calculating really an average speed, and that's just nothing but d over t. So I'll do the first row. The first row is nothing more than, again, keep tabs of your units. Again, if you remember, the basic unit for a distance is the meter, which we take as letter M. The base unit for the time is the second. And everything in physics, the basis of the equations of physics are all distance, time, and mass, right? Your base unit of mass in this class is the kilogram. And that's given by kg. All right, so in physics, every single thing is distance, time, mass. So you want later on, we talk about force. Again, I'm just giving you the rough version. Force is mass times acceleration. There's a sloppy version of Newton's second law. Well, force, we notice that force is in terms of newtons. However, we can look here and say, well, that's kilograms. And what's the acceleration? Well, that's meters per second, or meters per second squared. So yeah, you might say force is in terms of newtons, but newtons is a combination of what? Length, mass, and time. Or later on, we'll talk about energy, talk about what's called work. And the sloppy form of that is force times distance. So work, all energy is in terms of joules. Well, that's a newtons times a second. What's a newton? Kilograms, meters per second. So you can say that a joule is a kilogram meters squared per second squared. In general, is a joule. Right. Again, notice that even in the energy unit is in it's based on mass, length, and time, right? And so again, keep in mind what the units are. And so on that table, on the bottom of page 2 in the lab, I look at the first row. I mean, it's simply going to be what? I'm saying 150 meters divided by 10-second duration. So it's going to travel 150 meters divided by just 10 seconds. And so I would calculate 15 meters per second. The second row, I'll do one more for you, and then I'll let you do the rest. Again, this is first row. Second row of that same table on the bottom of page 2 of the lab. Again, V bar is D over T. What's my distance traveled now? 120 meters divided by 4 seconds. So you do that, you get 30 meters per second. So on and so forth. So in that table, you actually want to go through each of those rows. I'll let you do the rest of them. Each of those rows in the same manner. And then when you get done calculating all those speeds, indicate which one's the greatest. You can write, right next to the one that's greatest, you can just write greatest speed. So you kind of maybe to the row that has the greatest speed, you can kind of indicate it that's the greatest speed. All right, I'll let you do the other ones. And again, pretty straightforward, I hope. So you got to tell me which one's greatest, but you're gonna have to calculate all the rest of the rows. I'll let you do that. That's for the student. If I go to page 3 of the lab, page 3, you see a table. Okay, the table, if you look carefully, again, it's a grid. The grid is showing you distance over time, or distance versus time. So what you want to do in that table is essentially, as it says, you want to plot the values that are in table 2 with you want to plot the distance and the time. So again, it's like putting it on a 2-dimensional graph. When you took algebra, your vertical axis was always y and your horizontal was always x. Well, in this case, your vertical axis in this case is going to be the distance, and your horizontal axis is going to be the time. And so what you'll get some sort of a distance-time relationship. Let's say for your table, we'll say, let's say you have a D1, T1. I'm not going to put numbers here, but we'll just say, for instance, you go on your graph. Again, time should always be positive. So there's no negative time. There's no negative horizontal axis when it comes to time. Time is always positive. You look at this and say, well, this is my time axis. This is my distance axis. My distance is in terms of meters, and my time is in terms of seconds. So you go to your table. You go to that table 2 on the previous page, and you just basically put them on the graph. So for instance, I might say 10, 150, for instance. I'll put let's say up here is 150 meters, and over here is say 10 seconds, and so I'll put a point right there. All right, and then what do I want to do? Well, I actually want to draw a line from the origin to where that point is. All right, I'm going to draw a line, and let's say I do another point. And I can call this, I can say this is D1, T1, whatever. And you do another point. Let's say I have another point, D2, T2. Maybe it's the second point on this graph. So maybe I don't know. Let's see. I'll look at it. And it's 4, 120. All right. So if I say, okay, well, at 4 seconds, I go to 120. And, I stick a point right there. And I draw a line from the origin to that point. Right? And so I do that for all of these various points. And the idea is, this is a displacement, essentially, over a given time interval is I'm going from the origin to that particular location. And so what this is an indication of, it's the indication of the velocity. You notice that, if we go back to algebra 1, zero slope is along the horizontal, and as you increase your slope, you're increasing the velocity. You're increasing, essentially where as your line gets steeper and steeper, you're increasing the slope. Well, we know that the velocity is the slope of the position time curve. So a line that's steepest is going to have the greatest velocity, right? And so again, the steeper the line, the greater the slope. That's an algebra concept. So on a position time curve, the greater the slope, the greater the velocity. And that's what we're showing here. I hope I'm still on the whiteboard. I hope I'm still on the camera here. You guys see all these words? I'm not off the camera, am I?
No, you're good.
Awesome. Yeah, I fell off the camera a couple times in the previous lecture, so I want to make sure, try to measure things well here. So the idea here is that you're going to do all this. You're going to plot all the points in this graph, and then you're going to answer these queries. All right. And so again, as you progress, I've had questions like, what do I answer? Well, you read the lab carefully, and anytime you're asked to fill in something, you do it. Anytime you're asked a question, you answer it. So you have these queries. Which point on the line has the steepest slope on the graph? Which point on the line has the smallest slope? So you look at these various lines and you basically answer in a complete sentence what point it is. Which points lie in the same line? Well, none of them do. They're not. I found out that none of them were on the same line, because I found when I calculate all the various velocities, I don't see any of them having the same value. If the velocities had the same value, then they would be on the same line. The points would be on the same line. Number 3, using a graph, state a general relationship between the speed and the steepness of the slope. Again, as I just said, the speed is the slope of the position time curve. So again, this is, so again, number 3 on here would be what I've been saying all along. So query number 3, this is, for part A. What is the relationship? Well, what you should see is that speed is the slope of the position time curve. So if you take calculus, the very first calculus class you take is called differential calculus. I mean, literally, it is a study of slopes. It is an entire study of slopes. That's what the class is. So what I wrote on the board here is that the velocity is the first time derivative of the position. I mean, literally, it is the slope of the position. And calculus is all about the study of slopes. All right, and so the concept of a slope is an extremely important concept in science. The concept of a slope is a study of change. The only thing constant in the world is change. Things are always changing. All right, so you answer all 3 of these queries completely. All right, I'm going to now go to page 4 of the lab, and that gets us into part B. Now, part B we start talking about the relationship between velocity and time. All right. And so what should we theoretically, and again, in a lab, you always are trying to experimentally verify a theory. And so what is the relationship that I should see between velocity and time? Well, I wrote it on the board earlier, that kinematic equation. And so what I should see theoretically is this. Again, I'm on part B, page 4 of the lab. I mean, again, when you're doing an experiment, you're trying to verify something that is in the theory. I mean, again, that's what it is. You're always trying to, there's always this interplay between theory and experiment. That's how science works. That's how physics works. It's an empirical study. What did Galileo tell us? Well, Galileo said that we should see a relationship like this. Given that the acceleration is constant, we should see a linear relationship. That should be what we see. And that's what we're trying to see in the table here. In the table, you're noticing that you have table 3, you're noticing that you have a bunch of times, 0, 1, 2, 3, as the seconds tick off, as you go down the rows, and you see the velocity increasing. All right, and so what you want to try to do is figure out, well, what is the b divided by t? And so if you look at the table, I'll kind of do the first few here. In the table, you see time, and you see now we're talking about velocity, that relationship. Time ticks by, you got 0, 1, 2, 3, I'll do like 4 here. And you notice that the velocity, well, you start off, you start sitting still, but now you get an acceleration. Now, at 1 second passes by, you've moved 5 meters down the path. By the time 2 seconds passes by, you're now 10 meters from where you started. When 3 seconds passes by, you measure, you're now 15 meters down the path from where you started, going in a straight line because we're doing one dimension. As you let another second tick by, now you're 20 meters past where you were, and so on and so forth. You can fill this thing out. I mean, and so you look and say, well, what is b divided by t? So b divided by t, if you look at it, each one, I mean, this first one is a special case of 0, but you look at it and say, well, the first one is what? It's 5 divided by 1. What is that? That's 5. 5. What's the next one? That's 10 divided by 2. What's that? 5. What's the next one? 15 divided by 3. 5. 5, 5, 5. You notice that there's something constant here. I can imply from this graph that the slope is constant because v divided by t is constant, and I can imply from this graph that this is a constant acceleration graph. All right, and so I would imply from this graph that if I were to graph these points out, here's the velocity, here's the time, I would expect there to be a line. I'm 0, time is 0, I'm at 0, and I'm at some sort of line. The slope of this is acceleration equal to 5. What are the units? Meters per second squared is units on acceleration. Now, we have to be a little careful here, though, right? Is that our units are kind of funky. So our units are actually seconds right here. But this one is what? This is actually miles per hour. So in general, what you should have, if you do everything in SI, you should have distance per time squared. But here, it's a little bit different. What you're going to actually have is your acceleration is not going to be meters per second squared in this case. If you ask you kind of get a little tricky here. Query part B, query 1. And what units would you express acceleration in this example? Well, it wouldn't be meters per second squared. It would actually be meters per, or sorry, miles, actually, miles per hour second. That's what you actually have here. A little bit funky, a little bit different than usual. They're mixing in what we call the English units in here, right? The units we use in the United States. Everybody else in the world uses the metric system or system, le système international. We in the United States use the English system for whatever reason. So at any rate, that would be the crazy units for acceleration in part B, query 1. So let me ask you this: number 2, is the rate of change of velocity constant? Is the acceleration uniform? Well, I mean, again, when you answer a question, you never tell me just yes. In science, you always have to argue your answer. All right, so I'll tell you how I would answer this. I'm not going to just say yes. If you just say yes, I'm going to say that's wrong because you're not backing up with evidence. All right, so how I would answer part B, part B query 2 is I would say this. That's how I'd answer. Again, you're always on the spot in science. Okay, you always have to be proving everything you say. So if I say, is the change of velocity constant, is acceleration uniform? Well, I would say something like this: starting at time, starting from time t equals 1 second, the acceleration is a constant. Five miles per hour second. So yes, the acceleration is uniform. All right, so again, you don't just say yes. In science, you always provide a proof, or you always back things up with evidence. So again, in your lab, when you answer questions in the lab, again, I'm going to say this very, very clearly for those who are here and for those who will watch this video later. Anytime you answer a question in any lab, you must always back it up with evidence, or if you have an equation, you back it up with the equation. You try to back it up with all the evidence that you can muster, because that's what science is about. Science is about convincing a non-believing reader that what you're saying is true. Science is, basically convincing a peer reviewer that what you know what you're talking about, and what you're saying, you're convincing the audience, you're convincing the reader that it is right. That's what scientists are. Scientists are different than a lot of people in that, sometimes you're talking to an adversarial audience to some extent, or not I'm gonna say adversarial, but you're talking to an audience where you have to show and prove everything, right? And so again, that's the concept of doing the labs. You have to back it up with evidence. Not so much in the first lab, the data analysis lab, but any other lab afterwards. You're verifying. The job of the lab is to verify what I'm teaching in the theory. Don't believe anything I tell you. Again, the onus upon me as a scientist is to prove it to you. That's what labs are about. And then again, the third part is fill in the blanks with the appropriate numbers. Again, you can just put a little check mark there. That's what you've done. So this is query 2. Query 3, all I wrote down was a little check mark, because clearly I wrote the numbers down so you can see it on the table. I did it. So there's that's perfectly fine there. That's all right. So I'm going on now to page 5 of the lab. Now, 5 of the lab, we start talking about the other kinematic equation I wrote up on the board. Okay, I gave you the velocity equation, but I also told you there's a relationship between position and time in the kinematic equations. And let's remind ourselves what that was, as I proved it, and I derived it. It was the following. The displacement, x minus x naught, is the initial velocity times the time. You know, again, later, you know, at some time in the future, plus 1/2 at squared. Now we could say, for instance, if the initial velocity is 0, we know we have here is a quadratic relationship. So we can basically say, you know, for simplicity, like you see in table 4. In table 4, you know, again, I'm on page 5. In table 4, we're setting b naught equal to 0 in table 4. I mean, all that's saying is that initial velocity is 0. I mean, you look at the first row in table 4, at time t equals 0, the distance is 0. Actually, the table 4 is also telling you that x naught is 0 as well. So it tells you the initial position is 0, the initial velocity is 0. And so this equation simplifies a little bit. You know, I then have, you know, the position at some later time, x is just 1/2 at squared. Now, what I want you to do is it wants you to, you know, on this table, wants you to square the time. All right, and so in the table, you notice the time goes, you know, vertically 0, 1, 2, 3, whatever, 4, 5, 6, all the way to 10 seconds. On the right side, you just want to put the squares. The square of 0 is 0. The square of 1 is 1. The square of 2 is 4. The square of 3 is 9. You basically put the squares of the time that you're considering. Okay. Again, why do you care about that? Because that's what the equation tells you. The equation is a relation between what? The position and the square of the time. All right. And that's what you do. That's all you do in table 5. So you should see in table 5, you read down, you should see 0, 1, 4, 9, 16, 25, all the way to 100. You're literally putting the squares of the numbers 0 to 10. That's all you're doing there. Okay, I'm gonna go now. I'm flipping the page over to page 6. Page 6, you see a grid. In the grid, what you want to do is you want to actually plot the distance versus the time. Okay, and so let's kind of write up here what the equation that we believe is true that we're basically trying to verify. And that is, well, you know, the kinematic equation that we're kind of looking at right now is x is 1/2 at squared. So what we're going to do is we're simply going to just take this grid very carefully. And this is the distance. And I guess the distance is in meters in this problem. And the time is in seconds. And we're going to lay out the points. You know, distance is 0 at time t equals 0. At time t equals 1, the distance is at 1. At time at t equals 2, we find that the distance is, I'm sorry, not working here. Sorry, distance is 2 at time t equals 1. At t equals 2, the distance is 8. Or sorry, yeah. I'm sorry. T equals 2, the distance is 8. 3, 4, 5, 6, 7, 8, blah, blah, blah. And what you do is you'll basically plot out, and you'll see that you have you'll basically see you have a parabola. I'm not gonna put that name. My graph's not very good, but you'll see when you plot the lines, you have what's called a parabola, a parabolic relationship. Definitely not linear. I mean, linear means the highest power of an independent variable is 1. Clearly, what you see here is a 2. So there's a quadratic relationship between the position or the distance and the time here. All right. So in kinematics, there's a quadratic relationship between the displacement, I should say, and the time. And all you're really trying to do is you're basically very carefully making a plot of this on that grid that's given to you. And you want to make sure that when you do plots in this class, you take great care. You use a straight edge. You know, you don't just, you know, freehand it. You try to make the plot look professional. All right. Now, and then there's some questions. Again, you want to be very careful. Below that plot, number one says lay a straight edge. Does this data plot a straight line? Well, the answer is no. That it should not plot a straight line because it's not linear. It's quadratic. The data does not plot a straight line. So number one is no. It's looks like a quadratic relationship. Number two, the vertical lines are equally spaced, but the horizontal lines are not. Say the physical meaning of this in words. Well, essentially, you have you have an acceleration. So essentially, you're covering a greater and greater distance per unit of time. And so, the fact of the matter is there's not a direct proportionality relationship. The position is growing much faster than the time is growing. Hence why you're seeing a greater coverage in the displacement dimension than in the time dimension. And then number three, does the distance traveled during each interval of time change in a regular way? If so, explain. Well, you kind of look at it and say, well, what regular way would I see this distance changing? And what you kind of look at here is say, well, what would the acceleration be? What can I actually infer from this? Well, I can look and say, well, I can take a look at the velocity. For instance, I can say, well, I know that I know that the velocity can be equal to v naught plus, of course, v naught is 0, right? Which we're talking about initial velocity is 0, so the velocity is v equals at. So I should see, some sort of relationship. I can determine what a is by taking a look at the velocity relationship. And I say, well, a is whatever velocity is in terms of time. So I can look and say, well, I know that at velocity of, I have a velocity of 4 meters per second at 1 second. So I have 4 over 1, 4 meters per second in 1 second, or 4 meters per second squared. Well, what about at 2? Well, I have 8 meters per second at 2 seconds, or again, 4 meters per second squared. So I could look at this relationship and say, well, yeah, I do see a regular relationship. It corresponds to the equation x equals 2t squared. If you look at this and you say, well, if I take x equals 2t squared and I plot it, or I look at the values, at t equals 1, I get 2. Yep, I sure do. At t equals 2, I get 2 squared is 4 times 2 is 8. Yep, that's right. At t equals 3, let's see, I have 3 squared. Actually, t equals 3 squared multiplied, that's 9 times 2 is 18. Again, the velocity, the distance is 18 when at t equals 3. T equals 4. 4 squared is 16 times 2 is 32. If you look down, if you look at the table at t equals 4, you see the distance of 32. So yeah, it truly is following an x equals 2t squared relationship. Okay, so that's all you know for now. All right. Moving on, we're getting close to being done with this lab here. So what we want to try to do, and I kind of pointed this out in the data analysis discussion, is that if you want to really empirically try to determine what the acceleration is, let's say you're doing free fall, you're trying, and this acceleration of free fall would be g. If you're trying to do that, you really do yourself a favor by actually considering d versus t squared. What you do when you do d versus t squared, you actually will take this quadratic relationship, but to just change the variable, instead of considering it versus time, you consider it versus time squared. You actually linearize this relationship. You actually, when you do d versus t squared, you actually have a linear relationship, and the slope of that relationship would be 1/2 a, as I said in lecture. So in the data analysis lab. So look at. So what this next couple pages goes through is it kind of walks you through that. And so I'm not going to kind of go through this, but if you follow the steps, it's going to walk you through filling out tables 5 and table 6. All right, and so I'll let you kind of do that. But what I want to kind of look at is the bottom of page 7. Is bottom of page 7, you're essentially going to plot out the distance versus time squared. All right, and so if you look at table, going back to table 4 again, you notice that you provided a time squared variable. You calculated time squared yourself in the far right column. So what you want to do now, you can maybe do this in Excel if you wish, but you're going to want to now take the distance for each of those rows, same distance. You're going to want to plot it against the very far right column of time squared, which will be in seconds squared. Okay, so you're going to plot the second column, distance, but not versus the time, but the time squared. All right, and you'll notice when you do that, you'll get 0, 0. I'll give you an example, 0, and you get 0. For time 1 second, again, 1 squared, you'll basically get, the distance, corresponding distance, is 2. But, for time squared, the third row is going to be 2, 3. Actually, you won't get there until 4. Why? Because 2 squared is 4. And notice that at 4, your corresponding distance is going to be 8. 3, 4, 5, 6, 7, 8. And you'll notice that you'll put a point right there. And notice that as you continue doing this, again, your next one's going to be 9. You'll have all the way up to 18. So I guess 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Who knows what this is going to look like, but you have 18 at 5, 6, 7, 8, 9. And you'll see a point up there. And you should notice that if you plot the distance versus the time squared, you get a nice straight line. All right. And so what that's telling you is that you can linearize that relationship by not considering distance versus time, but distance versus time squared. And the slope, given that we know that x equals 1/2 at squared, if you're taking the distance versus the time squared, your slope of this graph will be 1/2 a. So when you do a laboratory experiment, let's say with free fall, you do yourself a favor. You're trying to calculate, if you're trying to measure g in free fall, when the acceleration a equals g, you actually do yourself a favor by making a linear plot, by basically plotting the distance fallen by the object divided by time squared. And what you'll get is the slope of that will be 1/2 of the gravitational acceleration. And that'll give you, and so multiplying both sides, multiplying by 2, you'll get g. You'll get a measure of g. So again, what this points out to you is linearizing the data by considering the distance versus the time squared. So you'll plot that data on the top of page 8, and you should see a straight line. Again, use great care to do this. Use a straight edge. Take care in your work. All right, I'm on the very end of the lab, and that's the queries. And you're going to want to answer all the queries. So again, query number 1, state the relationship between the distance and the time for uniformly accelerated motion. And what's the velocity versus the time? So again, I proved this to you, or I derived this for you on the beginning of this lecture. You would state query, this is part C, query 1. This is why you're doing this lab. What is the relationship? The distance is b naught t plus 1/2 at squared. Nothing is more powerful than an equation. An equation is more powerful than 1,000 words. If you have an equation, available, use it. Always use an equation if it's available to you. What's the relation for velocity? V equals V naught plus AT. Again, you're wrapping everything up you learned in this lab. You're proving what Galileo showed us, what I derived earlier. Okay, that, I mean, again, that is your answer to query one. The most important thing is your equations. This is worth thousands of words. Don't give me a big giant paragraph or whatever. There's nothing more important than an equation. All right, that's really now. Would the graph of the velocity versus time in table 4 be a straight line or a curved line? Let me ask you that question. I'm talking about query number 2. Would the graph of the velocity versus time in table 4 be a straight line or a curved line? What do you think? Anybody? Anybody want to straight line or curved line? What do you think for velocity? Is that this a straight line or a curved line?
Would it be a curved line?
It is a straight line. This is linear. So given that the highest power, this is a function, the velocity is a function of time. This is a constant. The highest power of the independent variable is 1. So that would be a curved line. I'm sorry, that'd be a straight line. This is straight. This is curved. Remember, the velocity looks like this. The velocity is a straight line. But the distance versus time is a parabola.
Okay, yeah, that's what I got confused.
Don't worry about it. So this is a curved line. That's a straight line. So velocity is a straight line. That's linear. The distance is in terms of time is parabolic. Now, distance versus time squared is a straight line. All right. So you would say it's a straight line because it's, because of why? Because of this relationship. Query number 3. What would be the numerical value in units of the slope of the graph? So what would you think what do you think the slope of the graph is? Well, we calculated it. We look at the slope of this graph. We calculated earlier to be 4 meters per second squared. Again, I did it by taking a look at the relationship with the velocity versus time. But again, remember I told you that again all of this is all depending on the data in table 4. I told you that I figured out that x was 2t squared. Well, what really is x? X is really what? 1/2 a t squared. So the acceleration should be 4 meters per second squared based upon my analysis. So again, that is the let me try to be a little bit neater about this, 4 meters per second squared. So based on my analysis, I'm looking at some object that's going at a constant acceleration of 4 meters per second squared. That's what table 4 tells me. That's what the ensuing plots from table 4, the plot on the top of page 6, the distance versus time plot, the parabolic plot, and the plot on the top of page 8, the linear plot with distance versus time squared, are both giving me that information. Okay, number 4, I'm going to ask you this question. Query 4, part C. What physical quantity would the slope represent in the graph from question 1 above? So regarding the slope of this graph, okay, so the graph in question number 1, again, what are we talking about? Well, we're talking about the graph in the top of the page. What physical quantity would that correspond to? So let's remember. So again, part C, query 4. We're talking about that graph that is the distance versus time squared, right? And that graph is what? It's linear. Now, remember that the distance is 1/2 AT squared. Again, I'm plotting the distance versus the time squared. So what is the slope of that? First of all, what is the slope of that graph? Remember, y equals mx plus b. What's the slope of that graph? It's 1/2 a, right? I mean, if I look at algebra, y equals mx plus b back in algebra 1, well, this is my slope. You know, again, what did we do in algebra 1? You know, we had a line, this was b, this is y versus x. This slope was m. So again, this is, now in this case, if b is 0, like in this case, then you just have y equals mx, right? You have y is, so you have the independent variable times the slope equals the dependent variable, right? So again, looking at this relationship, what do we have? Well, this is our y and this is our x, this is our m. This is our slope in this linear relationship. I've linearized it because I'm considering t squared as my variable, not t. All right, so this slope is 1/2 a. Knowing this, let's go back to query 4. What physical quantity would the slope represent in the graph in this graph? What physical quantity does that represent? What is a? What's a here?
Acceleration.
Absolutely. Not just the acceleration, it's actually the constant acceleration. Because, but it is, you are correct, it is the acceleration. But let's even be more specific, is that in the kinematics, all the equations we are considering, again, remember they're called the kinematic equations for constant acceleration. We're making the assumption that the acceleration is indeed a constant, which, as I said earlier, that's not a bad assumption, given that when we talk about Newton's second law, force equals mass times acceleration, you can certainly consider force being held over being constant over a certain time duration. While force is constant, mass is of course constant, then the acceleration is constant. And also, we have a really beautiful example of a constant acceleration called gravity. Acceleration due to gravity anywhere on the Earth is a constant. G is 9.8 meters per second squared, always accelerating all objects downward toward the Earth at 9.80 meters per second squared. So again, anywhere you go, you have a constant force field called gravity. So you have a nice example of a constant acceleration everywhere. All right, that's the lab. Again, it's a little bit of a marathon, but any questions? You guys are very quiet. Any questions? Are you guys good? You feel confident in this lab?
I'm good, thank you.
All right, awesome. Eduardo, you have any questions?
No, I'm all good.
Awesome. All right, well, if you don't have any more questions, I guess I'll call it a done deal. This lab will be due next Friday. So I guess what is today's the 28 till 29 plus, I guess it'd be February 5th, if I do the math correctly. So again, yeah, so labs for a given week are always due the Friday of the following week. All right. You guys have a good night.